Hello students. Let's talk a little bit about free body diagrams. Why do we have them? When we're doing some of our physics problems, it's not always helpful to have a picture that's disorganized and cluttered. And so the free body diagram sort of makes it easier for us because it simplifies the picture. It declutters it by getting rid of things that we don't need. And you do not have to be an artist because every diagram, the object is just a dot. And from that dot is where we draw all the forces that are acting on that particular object. So when we look at these different practice problems and we draw all the forces that come out from that dot, we want to find the net force. If our object is not moving, if it's at rest, or if it's moving at a constant velocity, then the net force will always be equal to 0. That's according to Newton's first law. If the object is accelerating, then the net force cannot be equal to 0. And we'll find out a little bit later that that would be conditions for Newton's second law. When we draw our free body diagrams, we're going to use some force abbreviations. So I've got a few of them listed here for applied force, frictional force, air resistance, gravity, which is just your weight, the normal force, which as you recall is also called the support force, and tension. So this is not a complete list. This is just the way that I write them down, so when you see the examples, you'll know which forces that I'm referring to. So I'm going to put on the screen next a couple of different practice problems that we'll do for free body diagrams, and then I'll walk you through how to do them. Okay, let's do our free body diagram problems. The first three have to do with a car that's moving. So we'll just draw a dot that represents the car. We can't turn gravity off, so we always have that force acting downward. And we have the normal force upward. So in the first problem, it says that the car is moving at a constant velocity. So that means that there's some force that's applied to it. The engine is pushing it forward, and then the frictional forces are pushing backwards. So the opposite forces are going to be equal. In this case here, gravity and the normal force are equal. The applied force and the frictional force are equal. The net force that's acting on the car is equal to 0. In our second example, we take the same car. Again, we draw the dot. Gravity is acting downward. The road's pushing back up. That's the direction of the normal force. But in this example, we have an accelerating car. So if the car is accelerating forward, then the applied force, Fa, needs to be bigger than the frictional force. So in this case, the net force is not equal to 0. In the third example, we now have the car that's coasting to a stop. Again, gravity is downward. The normal force pushes back up and it balances gravity. But in this case, because we're coasting, I'll write it out here, to a stop, the velocity of the car is forward, but the acceleration is backwards. We're decelerating. So we have no force that's pushing the car forward anymore. We just have frictional force that's pulling backwards. The net force in this case is not equal to 0 because we have acceleration. In the last example that we have a parachutist at terminal velocity. Gravity is pulling this person downward. And we've got air resistance, FAR, upward. Those two are balanced because if it's terminal velocity, this person is falling at a constant velocity downward. The net force that's acting on this person is 0. So here's 4 examples of how we can draw free body diagrams. And I will see you in class.